ScagnosticsJS extended scatter plot visual features for the web by Vĩnh Phạm and Tô Mỹ Đặng from Interactive Data Visualization Lab, Computer Science Department, Texas Tech University. Scagnostics is the set of features that characterize the data distribution in scatter plots. There are 9 scores in Scagnostics, including of outlying, skewed, sparse, clumpy, striated, convex, skinny, stringy, and monotonic. However, there is no formally published implementation 3D or higher dimensional Scagnostic. This project aims to provide Scagnostic implementation in JavaScript called ScagnosticsJS and also extend these measures to 3D and higher dimensional scatter points. Binning. Binning helps to reduce the computation expenses. There are 2 standard ways to bin scatter plots, hexagon versus leader bins. In 2D versions, we provide users option to choose either binning methods. In 3D and ND versions, the binning algorithm is leader bins. 2D implementations. In 2D implementation, these are the 6 main computation tasks. First, normalization. Second, binning. Third, triangulation. Fourth, building minimum spanning tree. Fifth, finding the degree 1 and 2 vertices. And finally, finding convex hole and concave hole. With these 6 main computation tasks, we will be able to calculate 9 Scagnostic measures out of them. 3D implementations. For 3D implementations, MST-based scores such as outlying, skewed, clumpy, stringy scores. They rely on distribution of MST edge lengths and the conclusions remain the same as in 2D implementation. For the sparse score, it's also calculated based on MS3 edge length distribution. However, when the dimensions increase, it is possible to get the values which is greater than 1 for this score. That's why its implementation will be discussed later in ND version. For outlying, skewed, clumpy, and stringy, these are 3D typical scatter plots for them. 3D striated score. Striated patterns includes parallel lines, smooth lines, and parallel planes in 3D. Striated score is revised to count on the angle between adjacent planes formed by every 3 consecutive MST edges. So in 2D version, they only consider the cosine theta between every 2 edges of the MST, which is smaller than minus 0.75. However, in 3D, the corner between the planes of the 3 consecutive edges will also consider the cases which cosine of the theta, which is greater than 0.75 as well. That's why we need to use the absolute signs over here. To clarify this case, we add 3 examples over here: 2 parallel planes, 4 parallel lines, and a smooth line. For 2 parallel planes, if we don't use the absolute sign, the score is 0.53, 0.65 for a 4 parallel line, and 0 for this smooth line. However, if we apply the absolute cosine to consider for this case, then the score will be 0.85 for the 2 planes, the 0.92 for the 4 parallel lines, and also 1 for this very smooth line. This one is more reasonable. Convex and skinny scores in 3D. The convex and concave holes calculations in 3D are similar in 2D, except the line is conceptually converted into plane, and the radius for the circle used to calculate the alpha hole becomes the radius for the sphere in 3D. And also, the convex now, instead of considering the area, we need to consider the volume for the alpha hole and the convex hole. And also for the skinny score, we consider volume and the surface instead of area and the perimeter. Also, we adopt the constants here to make sure that the sphere will have the skinny score of 1. Here are 2 exemplar plots for convex score in 3D and skinny score in 3D. It is also worth noting that we adopt the algorithm from Robert Nuremberg to compute the volume from 3D holes from its set of faces. This is very efficient algorithm. Monotonic score in 3D. The monotonic score is calculated via the partial collision among the 3 variables. So we take the maximums of the partial score of every pair of the 3 variables. Here is an exemplar sample plot for monotonic score in 3D. And the implementation. In ND, outlying, skewed, clumpy, and stringy scores rely on the distributions of MST lengths, thus their conclusion remain the same. Monotonic score is calculated via the partial correlation of the variables. Here are the exemplar plots for outlying, skewed, clumpy, stringy, and monotonic in higher dimensions. The sparse score was originally calculated as Q90 of the MS3H length. When the number's dimensions n increase, this value can be greater than 1. Therefore, in 3D and ND versions, this value is normalized to put dimension n into account. The sparse score now is divided by 2 times of the dimensions over 3. This one is to guarantee that the value would not get over 1 and it's gonna be compatible with the 2D version too. To clarify this one, we give an examples of 2 synthesized sets of points in 6 dimensions and 10 dimensions correspondingly. The twos are very similar except that one has 6 dimensions and another one has 10 dimensions. If we simply use Q90, then the first one will have sparse score of 1.76 and the second one will have a score of 2.17. And if we do outline the normalizations factors over here, then the sparse score for both plots get into 0.88. This one is a reasonable number because the two plots are very similar except for different numbers of dimensions only. Convex and Skinny scores are based on the convex and alpha Hall calculations, which have performance constraints in higher dimension. Even with approximation, these calculations are exponential to dimensions and vertices inside the plot. Therefore, we do not provide convex and skinny scores for this current version of the ND implementation. Similarly, striated score, there is no cross product of two vectors with dimensions higher than 3. There is not often much reason to use lines and planes in high dimensions as well. So there is no such information about corners between lines or planes in NDs in the space with more than 3 dimensions. Therefore, at this time, we do not provide implementation for striated scores either. ScagnosticsJS evaluation. We evaluate the ScagnosticsJS implementation with 6 real-life datasets. They are US employment rate, US employment net change, prevalence of HIV, unemployment rate, world life expectancies, New York stock etchings. These are their corresponding exemplar plots. Currently, the time-consuming computation tasks are triangulation and building the minimum spanning trees from the data point, while calculating score is fast. Furthermore, we also generated a set of synthesized plots for each of the targeting Scagnostic measures. It's worth noting that the score for the measures that the plots target are flat with higher values for 2D versions, for 3D versions, and also for higher dimensions. Use cases. To demonstrate the usefulness of ScagnosticsJS, we also apply it in monitoring critical variables of a high-performance computing center. First, we use 2D version to monitor CPU temperatures and fan speed for compute in this center. We compute the outlying contribution for each compute at a time step as the difference of the outlying score of the whole set of computes at that time and the outlying scores of the same set of computes when leave that single item out. The red computes are those with outlying score contributions higher than a threshold. Also, the performance of ScagnosticsJS allows us to do this calculation in real time for this monitoring task. This also shows its usefulness in detecting several of abnormal events happen in these HPC centers. Please refer to these papers for further details about this use case and this application. We also use ND version to monitor variables critical to these HPC centers such as CPU temperature, fan speed, memory usage, so on and so forth. Similar to the previous use case, we also use leave one out strategy, which is to calculate the overall outlying score at a time step and comparing to the score when leave one compute out to know its contribution to the overall outlying score. Also, radar chart now is used to visualize a 9 dimension instead of the 2D scatter plots. We currently use Euclidean distance as the distance matrix, but other options such as L1 or Lk, where k can be a fraction, should be explored as well in the future. This application has to monitor the 9 critical variables well. For instance, in this case, it has to highlight the compute 62 with high values of almost all the variables. On the other hand, the compute 850 is having low values for these variables in this period of time. These events are important in this center because it helps to suggest the system administrators to check on these special nodes. It also helps to indicate the load balancing issues in this center. Please refer to this paper for further details about this event and these applications. ScagnosticsJS Implementation. The ScagnosticsJS API reference can be found in this link. There are 2D, 3D, and ND versions of this as well. Furthermore, we also provide Scagnostic Playground as an online demos on which you can explore underlying Scagnostic calculation processes and the visualization of their intermediate results as well. They contain example scatter plots for each of the 9 Scagnostic mentioned. You can explore all of the calculation stages via these links. From here, you can find the API references, including the 2D, 3D, and ND versions as well. You will know how to install them, how to download them, or how to use CDN version of the library. There will be user manual and also code snippets as well for each of the versions. Furthermore, you can click on each of the links over here to explore the underlying computations of each version. Let's say this one is an example of the outlying scatter plots, and you can try to do the binning. Also create the triangulations. Then building the minimum spanning tree from the triangulations. Also finding the outlying links. Okay. Also finding the outlying points. You can find the no outlying points. Then you'll find the V2 corners over here. And also you can calculate the convex hole and also the concave hole as well. So this will help you to calculate the Scagnostic scores. Similarly, you can explore the 3D versions of it or the ND version of it. Thank you, and if you have any questions you can address now, or please contact us at ttu.edu and Tomidang at ttu.edu as well. And here is a list of the references to the papers about our use cases. Thank you for watching.